Next, we will take a look at this page, problem number 7. We have a box being pushed by a girl across the carpeted floor at constant velocity. Let's highlight one thing right here. Constant velocity is absolutely a clue that the force is balance. And I like to write a shorthand for that by saying that the net force equals 0, like that. So now let's draw a free body diagram and determine the force the girl pushes the box with given this coefficient of kinetic friction. So first, we have the normal force, which is the force from the floor acting up on the box. We have the weight of the box, or Fg. We have an applied pushing force. And of course, we have the friction force going backwards like this. So we've got a couple parts to this problem. First, let's balance forces vertically. So we have Fn minus Fg equals 0. And I want to be clear. The reason Fn and Fg balance is that the box doesn't suddenly jump up into the air, nor does it accelerate and sink into the earth. It's the fact that vertically the box doesn't move at all. It does move horizontally, but vertically there's no movement at all, and that's how we know the vertical force is balance. So we can now plug in a couple numbers to get the normal force. So the normal force is going to end up equaling the weight, which is m times g. And so when we solve for that normal force, that's going to end up being 20 kilograms times the 10 meters per second squared for the acceleration due to gravity. And that's going to give us a 200 Newton normal force. We're going to use that in a second. Now, speaking about the horizontal direction, we have the applied force, Fa. Now, a rule. Always subtract off friction. And those forces balance, hence they equal to 0. They balance out and equal 0. And just to be clear, let me say it one more time. In our introductory physics class, this class, please note that the friction force that is applied points backwards and is always the force that we subtract in beginning physics. There are more advanced physics problems where you don't subtract the friction, but for our purposes, we think of the friction as always trying to slow us down. And so we're always going to subtract it in the problems that we do. So we have an applied force that is going to exactly equal the friction force. Now let's go ahead and calculate that friction force using the formula. The friction is mu kinetic, which is the coefficient of kinetic friction, times the normal force. And that's going to be 0.1 times the 200 newtons we calculated right here. And so we're going to end up getting a 20 Newton force. So what that tells us is that the applied force is 20 newtons. Excellent. Next, now suppose she pushes with the same force, but there's an acceleration of only 0.5 meters per second squared. Calculate the new friction force and the coefficient of kinetic friction that would give this acceleration. So we are going to note a couple things. Nothing changes in the vertical direction. So Fn is still 200 newtons. And in the horizontal direction, we now have, and by the way, I changed this number. I think C period, I gave you a different number. I'm going to use 0.5 for the acceleration because I think with the numbers that I gave you, there was no friction acting. So I wanted to do an example where you actually do have a friction force and a new kinetic coefficient to calculate. So we have the applied force. We have a new friction force that we're going to calculate in a second. And that's going to equal m times a because now the forces are unbalanced. And we know they're unbalanced because we're accelerating. So we're going to have 20 newtons from above minus our unknown friction force is going to equal the 20 kilogram mass times its acceleration. So when we isolate that, we're going to end up getting a friction force equal to 10 newtons. And now we can put these two ideas together right here to get the coefficient of kinetic friction, the new one. So that's going to be mu k times the normal force, and that's going to be 10 for the friction, which we just solved, times mu k times the 200 newtons that we calculated up here, again in the vertical direction, nothing changed. And so we're going to end up getting a coefficient of friction equal to 0.05, like that. Last, the girl lets go of the box, but the friction force in B still acts on the box. We want to determine the acceleration of the box now. So I'm going to actually redraw the free body diagram. So I'll have a normal force. I'll have the weight force, or the gravity force, or the force of gravity, due to Earth pulling on the object. We have the friction force right here. Now we have no applied force because we cut that force off. So if we want to set up the equation, we would say 0 minus the force of friction equals mass times acceleration. And we have a 10 Newton force here, so negative 10 equals 20 times A. And when we isolate, we're going to end up getting that the acceleration is negative 0.5 meters per second squared. And that is our problem number 2, or rather, page 2, problem number 7. We'll take a look at the third page in the next video.